What's up, everyone? Welcome back to another exciting day of proof, set theory, and logic. Thank you for that. That mic is still a little loud. Let me fix that. There we go. That's better. Okay. So thank you for bearing with me with the canceled class on Monday. I was nightmarishly sick. I'm still feeling kind of rough, so we'll see how everything goes. Quick stuff before we get started on talking about functions some more. First off, thanks for all the homeworks. I think everything that people have submitted so far is graded. I really do want to encourage you all, though, to look at your work and compare it to what's in the answer key. So one of the things that I want, hopefully, to do with homeworks being as they are is encourage you to get some practice reading proofs and assessing whether or not they're good, since that is probably one of the best things you can do to improve your own proofwriting skills. I encourage you to think of yourself, and I don't mean this in like a mean way or anything like that, but think of yourself kind of like you're in like second grade, right? Like in the mathematical sense of like, you know, in terms of the content you're covering, like you've gotten used to, like in second grade, you've gotten used to like the letters and stuff. You understand like the sounds they make and everything. You just kind of got started reading. And what they have you do a lot of is they have you practice like writing something or reading something and then like assessing whether the thing you read makes sense, like what it's saying. Write something, then look at what you've written, like figure out mistakes you've made, figure out what you're saying, like what it's said or what you've written, what it says. Does it say the thing that you wanted to say? All this kind of stuff. Think of it like in a similar way. Not like, you know, like, oh, you're second graders, like you're way behind or something, but like in terms of proofwriting, this is probably for many of you one of your first experiences with it. And so in that sense, it is not that different from being in like second grade, right? So since it would be probably, well, it would just be more homework if I just gave you proofs and I was like, read these proofs and tell me if they're good or not. Like I'm not giving you proof reading exercises. I'm giving you proof writing exercises. My goal is to have the checking of your work function as the proof reading exercise. That way, I don't have to assign you like a separate, like here's proof writing problems, here's proof reading problems. Instead, the reading problems can be reading the key and reading your own stuff and comparing the two and trying to understand it. So I really encourage you to go through and do that. Look at the keys, look at what you have, try to assess whether or not they're saying the same things or if they're different, they capture the same ideas. And then if you have questions, please let me know and ask for feedback. This is probably relatively different than what you've had to do in most other math classes. And in some ways, I get why that is. You know, like in more computational classes, generally you turn in your assignment and like that's the end of it. You just get a score back. OK, there you go. You can look at it if you want, but you know, OK, a lot of people don't really, right? That is, for the most part, we've kind of trained you up until this point to be relatively, like we've encouraged you to sort of be like lazy and like looking at your own work. Not that I'm calling you lazy, but I'm just saying like there's no real reward for it, right? Like all it is just more time spent. And if you do poorly on an assignment or something, yeah, you can go back and look at it, but probably the best thing to do is to spend more time practicing. And that's what most people will end up doing. Instead of going back over their old work and trying to figure out what went wrong, they'll spend more time practicing. And if you did well, then, well, there's no reason to look at it. So we really have kind of encouraged you up until this point to spend almost zero effort, like going, like there's no real benefit to you so far, right? But hopefully here you can take, have it be well incentivized, at least in the sense that if you don't do this, then you might get blindsided on the exam, right? So I don't know, hopefully at least I've provided a positive incentive for you to practice proofreading as well. So do that, and then if you look at your stuff and you look at the key and you go, I've looked at them and I can't actually tell, let me know. I will provide as much feedback as you want. I'll provide very detailed feedback. I'm not individually grading problems to try to get out of giving you feedback. I will provide as detailed feedback as you want. But I want you to practice that. So please do. Give it a shot. I think you will benefit greatly. Cool. So last time we were talking about functions. Let's think about a few functions. So to pick back up, let's talk about a couple of common functions. If you actually, really quick before I jump into an example, let's do a quick recall since we ended with this, and I want to remind everyone, since it's been a little while, a function is I'll say a relation from a set A to a set B, i.e. a subset of A cross B with the property that every element of A appears as the first entry in one and only one ordered pair in the relation. So, another way of thinking about this is just that functions are subsets of Cartesian products with the property that if you covered up all of the second coordinates, you would just have the set A with no repeats. Cool? All right, right on, functions. Notationally, if f is a function, then we write f of a equals b if the ordered pair AB is in F, which looks weird to write as is in F, but the idea is that a function is a subset of ordered pairs. So it's perfectly reasonable to talk about an ordered pair being in a function. We just don't normally write it like this, right? That is, when we say f of a equals b, we're treating f like it's this little device that you can feed a's to and get b's out of, right? It's a gumball machine, and you put your a in and turn the handle, and a little b comes out. Okay, fine. That's a nice way to think of it. But in terms of how we've defined it, it is sets of ordered pairs. We'll just borrow this kind of mechanistic language to make it easy to talk about without having to just have ordered pairs flying around constantly. It makes many concepts much easier to express. All right, cool. So here, let's warm up with a couple common types of functions. Here are a few common functions. Okay, 1. Let A be any set. The identity function, which people will often write as like a I, well here I won't use an iota, I'll write it just as like I, from A to A is defined as I of A is equal to A for all A in big A. Cool. All right. Now there's other functions that are very similar to the identity function that you may confuse with the identity function if you're not careful about it. That is, the identity function sends a set to itself. If A is a subset of B, then the embedding of A in B is the function, I'll write it as a little iota that sends A to B, defined by iota of A equals A for all A in A. Notice this is a different function. Why? All of its ordered pairs are the same, right? But it lives in a different place. That is, iota is a subset of A cross B, while the identity is a subset of A cross A, right? They have the exact same values, but the values live in different places. That is, the codomain of the embedding is a larger set than the codomain of the identity. Yeah? So that's kind of a fun, similar to an identity thing that you might come across. Okay, embeddings, identities, nice. Here's another nice type of function. Let A and B be sets, and let B be some element of B. A function, let's call it K, from A to B, defined as K of A equals that little b for all A in A, is said to be a constant function. That is, its values don't change. So you can have constant functions. Classic examples of constant functions that you've probably seen from algebra include things like flat lines. F of x equals 4, something like that, right? Classic example of a constant function, but it doesn't need to be from the reals to the reals, right? Anytime, you encounter constant functions all the time in your day-to-day life, but you don't think about it, right? Like if you say, all right, we've got you know, if you're passing something out, like you're like, everybody take a test, right? That's a constant function. I'm mapping people to tests, and we're all getting the same test, right? The output for each person is the exact same thing. It's the same test, right? If I give out tests that have different questions to different people, like I have 2 different sets of questions or something like that, and I pass the test, then that's a non-constant function, right? So you can see these sorts of things all around you. Fun. All right, constant functions, easy enough. What other types of common functions might you encounter? What named variants of functions do you frequently see? Here's another one. So here's a nice and easy one. Let A and B be sets. The coordinate projections, I'll go a little further. We'll write them as pi A from A cross B to A, and pi B from A cross B to B are defined as, well, pi A takes a pair AB as input and just spits out the part that lives in A, while pi B takes a pair AB as input and spits out the part that lives in B, and this is how it works for all AB in the product. Naturally, you can imagine if you had like triples, right, instead of products, but you have like, ordered triples or ordered quintuples or septuples, whatever you want. You could define a projection on each coordinate. Yeah? Kind of nice? Okay. So projections are kind of the obvious, hey, you've got a pair of things. What if you just took one of them? Yeah? Nice. People also sometimes write these as like, if they don't want to reference what the sets are, they could just say something like proj for projection, and write like proj1 for the projection onto the first argument. Since ordered pairs have a first and a second thing, you don't necessarily have to reference which set the first or second thing lives in, right? So people might sometimes write proj1 instead of pi A, might write proj2 instead of pi B. Okay, but just different notations for the same thing. So projections, cool. One nice thing to think about with projections is that we actually effectively define functions in terms of projections. Yeah? That is, when is a relation a function? Well, it's when you've got, so if f is a function, then, well, here, let me think of it, let me write it like this. So if f sends a to b, and it's a function, then proj 1, or if we want to talk about it like this, we could say pi a of f must be equal to, or so writing it this way, I'm actually doing something else. I'm talking about, let me write it this way, pi of ab for ab in f. This should be equal to a. Yeah? So if you project all of the ab's in f onto their first coordinate, you should get back a. And moreover, you have the property that pi a of a1b1 equals pi a of a2b2 implies that b1 equals b2 for all ab, a1, I'll write it this way. I'll actually write it and say it. For all a1, b1, a2, b2 in f. So that is, it hits everything in A, and it hits it only once. Yeah? If you look at it like this and you say, hey, here's the definition of a function, you need these two conditions, wow, it makes functions look worse, doesn't it? Right? I think it is much easier to think of functions in terms of a blob, and everything over here has arrows going out of it, you know, just something over there, and nothing has two arrows going out of it. Yeah? I think that's a way easier picture to imagine. So that's how I like to present it. But if you wanted to write it in terms of other relations, defining relations only in terms of relations and not appealing to our vague intuition for blob diagrams, I guess, you'd have to do it like this, which does not quite feel as easy or intuitive. But hey, why not? You could do it. OK. Here is another type of function you can look at. So you could say something along the lines of, all right, what about this? So let A be any subset of the reals. The characteristic function of A is the function chi A from, and now there is a great degree of variation. Either you're going to define it as the characteristic function sends R to R. Basically, there's a lot of differences in terms of what people use as the codomain. Some people might write it as chi A from, I'll write it from R to R here. Defined via chi A of x is equal to 1 if x belongs to A, and 0 if x is not in A. OK, notice, since it only takes on the values 0, 1, you could just as well say chi A has its codomain, say like 0, 1, just that set. Or its codomain could be the integers. Or its codomain could be the rationals, or its codomain could be the complex numbers. Any set that contains 0 and 1 in it would be a perfectly reasonable choice. I more frequently see it written like this, just so, you know, it lets you break down a function into nice pieces or something, right? Like write a piecewise defined function in a nice way. That is, if you have, say, like a function where you're like, hey, this function is, I don't know, it's like, x squared if x is less than 0, and it's x plus 1 if x is greater than or equal to 0. You're probably used to seeing stuff like this from like Calc 1 or something, yeah? Okay, notice you can write this function as f of x equals x squared times the characteristic function of the interval from negative infinity up to 0 plus x plus 1 times the characteristic function of the interval from 0 on over to infinity. Since this one will be 0 as soon as you move outside of that, and this one will be 0 as soon as you move outside of that interval, right? Characteristic functions are kind of nice because it lets you break down a piecewise function in terms of just a sum of functions multiplied by characteristic functions. Kind of nice. Okay. Notice you don't need to have this be a subset of the reals either. You could talk about characteristics functions for any set, yeah? You could say let A be a subset of B, and then you could take the characteristic function for A, which says, hey, sends all the B's over to the reals, and it's defined in exactly the same way. You can make characteristic functions for any subset of any other set. Perfectly reasonable. They're just indicators. They're, is it in it or is it not? Yeah? Okay, nice. So characteristic functions. I will leave that as R for now, though, so it doesn't feel like I've switched up the definition on you. But my point is that you can do this sort of trick all over the place. All right, cool. Fun. There are lots of other name types of functions that you might encounter over your mathematical career. These are only a few of them. But yeah, what do you think? Kind of nice? Kind of reasonable, perhaps? Okay, fun. So, side note, try to think about characteristic functions really quick. What does, for instance, the graph of a characteristic function look like? Yeah, graph of a characteristic function will be like flat, and then it will go up to 1, and then be flat, right? Or, you know, maybe actually it's like 1 forever after some point or something like that, right? What would say, ooh, here's a good question. What about the characteristic function of the rationals? What would that look like? Oh, that's a really hard one to graph, isn't it? It's 0 at every every irrational number and 1 at every rational number. But wait, aren't there lots and lots of both of those? Aren't they kind of interlaced together very closely, right? Oh man, it would be like almost like static, right? Yeah. Ooh, that's an interesting function. We'll come back to that. So that is a great function to showcase certain types of pathological properties. Okay, fun. Here's another type of function that you'll encounter that is very important, and indeed you've encountered it many times already. Binary operations. This is section 5.1.1. Here's a quick definition for you. So, a binary operation on a set, let's call it X. I'll call it capital X. So I'll put the bars on it since capital and lowercase x's look almost identical. On a set X is a function. Let's just call it star for right now. I don't mean multiplication. I'm just calling the name of the function an asterisk. So it takes 2 copies of X. See why I want to have the distinguishing between the capitals and the lowercase. And it sends it to 1 copy. Okay. If star is a binary operation on X, we write a star B to denote star of AB. that is, if you, I'll even call it equals C. How about star AB equals C to denote that if you plug AB into this function, you get back C. Yeah? So we'll write it in between two things, since it always takes pairs of stuff, and it gives you something back. Okay, can you think of some examples of binary operations that you've perhaps seen before? Multiplication, yeah. Addition? Subtraction? Yeah. Fractions, division, right? You know, okay. Lots of binary operations, kind of nice, yeah? Okay, so these guys come up all the time. This is the bread and butter of arithmetic and algebra. Nice. So, easy example. Addition, multiplication, subtraction, and division. I'll say with a catch, since you have to be careful about dividing by 0, right? Are all examples of binary operations I'll say on appropriate sets. So that is, addition is a binary operation on the integers. It's a binary operation on the natural numbers. It's a binary operation on the reals, on the rationals, on the complexes. I won't write all of those as separate examples, but you should also be careful to make sure that what you're saying makes sense. For instance, is subtraction a binary operation on the naturals? No. For instance, 2 minus 7 is not a natural number. It's minus 5, right? That's not a natural number. So you should be careful. Not every arithmetic operation is a binary operation on any set. You have to make sure that the thing you get out also lives in the same set that you're taking your original two things from. Yeah? This is the same business with division, right? You have to make sure that you get rid of 0, right? Okay, cool. So, fun. All right. So that's a good example there. I guess I have a second space for an example right here. So let me just write what I said there. Subtraction is not a binary operation on the naturals, since, for example, 7 minus 12 is not a natural number. Okay, so binary operations. We've seen them, we know them, we love them, they're great. Sometimes binary operations have good properties that we like, and if you take an abstract algebra course, you will talk about many of these properties in great detail and see all of the richness that comes out of having a set with nice binary operations. So here's a few different properties you might see. We say that a binary operation, let's call it star, on a set X is, and here we'll do two different things. One, commutative, if x star y equals y star x for all ordered pairs x, or I'll even say just x's and y's in X. That is, if the order doesn't matter. Yeah? Okay. And we could also talk about associative. If you can chain it together really nicely. x star y star z is equal to x star the quantity y star z for all x, y, and z in big X. So commutative, doesn't matter what order you do it in. Associative, I guess, yet again, it also doesn't matter what order you do it in, but I mean that in a different way this time. That is, commutative says it doesn't matter which one you do first if you're doing it on a pair of things. Here, if you have a pair of binary operations, it doesn't matter which one you do first. Yeah? Cool. So they both are just different versions of saying, doesn't matter what you do first. All right, fun. Cool. So what are some good examples of commutative, associative, binary operations that you've seen before? Are addition and multiplication commutative? Yes, at least in terms of real numbers, complex numbers, all that kind of stuff, right? Okay, good. What about, so who here has taken a linear algebra class? Some people. What about matrix multiplication? Is that commutative? No, it is not. Okay, so there are commonly encountered versions of binary operations that are not commutative. What about subtraction? Is that commutative? Is 1 minus 2 the same as 2 minus 1? No way. Okay, so subtraction, also not commutative. It's really fun to see this. Like once you see some of these basic properties, you start to go like, oh, okay. That's why, for instance, when you are a little kid in school, they teach you addition first because you don't have to worry about messing up the order, right? But as soon as you get to subtraction, then suddenly it's a little tiny bit harder because now the order matters. Oh, okay, you've like doubled the number of things you have to know, right? Since you have to know each different order of it. Oh man, okay. So tons of different good examples, lots of different classic examples. Let's look at one maybe that's unfamiliar and see if we can get any sense of what's going on there. So here is a question to you. Define the operation star on z via the following. A star b, let's set it equal to ab, multiply them together, and then square the result. Is star, is it commutative? Does it commute? What do you think? Let's find out. So how would we do it? Well, I would say let's start out with a star b. Well, we know what that is. That's ab squared, yeah? Okay. Now, if I go ab squared right here, and I just use, well, perhaps I am using something that I have not yet perhaps described and said, oh, look, squaring is the same as multiplying twice, right? Maybe I should be careful since we haven't, described squaring in the same way we have just talked about multiplication. But if we're just using this as shorthand, okay, cool. We could do it like this. So then we could say, hey, look, multiplication of integers is certainly associative, isn't it? Okay, so I could do this. I could go, hey, this is A, B, yeah? And I could do a flip. And I could go, oh, it's also commutative. Yeah? And now I could use associativity again. And I could flip this around and I could go, okay, AA. And now this is B. Yeah? And then I could use commutativity of multiplication again and flip it about. Yeah? What do we want to get to at the end? I'm writing this out in perhaps painful detail. Let me show the, we'll go, at the end of the day, what do we want to get to? What we want to get to is equal to B star A. And B star A would be BA squared. BA. So what I have now done is, oh no, I should have flipped this there. That's what I should have done. Yes, I should have done that. Okay, yeah, here. I'll make this faster by doing this. So now I can flip these two and get BA, AB, right? Just by grouping, right? Okay, and now I can regroup and then flip again. And then I can go, hey, look, BA, and by commutativity of multiplication, BA. And then I can go, hey, look, this is BA squared, just like I want. And writing this slightly higher up on the board, we have, look, B star A. Yeah? So if you want to be all wild and overly detailed about it, you can justify each and every step by bringing it through like this and going, hey, okay, cool. And really what I should do right here is also have extra parentheses to be clear which order I'm doing all of the multiplications in. But yet again, what I guess I'm trying to say is that, look, I've created a new commutative binary operation by using an existing commutative binary operation, multiplication. This is just a bunch of multiplication. Yeah, the squaring is just a convenient way to write more multiplication. Okay, so you can imagine that anytime you've got a commutative binary operation, if you just repeatedly apply it, you can create new commutative binary operations. Nothing too crazy. All right. Well, what about associativity? Is this associative? Let's ask ourselves that question. And then perhaps we should be done for the day, because we're getting, well, no, maybe not. We might have time for a little bit more. Is this associative? Well, what we'd have to have is A star B star C equal to A star the quantity B star C, right? So what is this? Well, this is AB squared star C. That's what A star B is equal to, right? And so if we write this out, well, what do I get? I get AB squared times C, that whole thing, squared. Yeah? Now, on the other hand, if I do A star B star C, well, then I get A star BC, that quantity squared. And this is just A times BC squared, that whole thing, squared. And all we have to do now is look through it to figure out what's going on and say, hey, over here, what is this? Well, this is A squared B squared C squared. Well, on the other hand, this right here is A B squared C squared squared. Are these going to be equal? No. Uh-oh. Multiplication is an associative binary operation. What the heck happened here? I just chained together multiplications. I chained together some associative binary operations, but I produced something that is not associative. So maybe this is more complicated than you might expect, right? It is not the case that when you just chain together operations, you automatically preserve all of their properties. So, not associative. So if you want to study binary operations on sets with various levels of properties, you might say, like, I want an associative binary operation on a set, and I want there to be an identity element. An element which, if I use it with the associative binary operation, does nothing to the other element. Okay, then you would have a type of object that you can study. People might call these monoids. Yeah, I believe monoids, yeah. Monoids, if you get rid of the identity element requirement, then you would just have a semi-group. If you just have a binary operation, you would have a magma, I think people call that. But if you have commutativity, you might get some nicer stuff. You have a commutative monoid, a commutative semi-group, and all this stuff. Okay, whatever. This is all what you would do in abstract algebra. We're not in an abstract algebra course, but we will encounter some of these basic things. If you find it interesting and fun to think about, then I encourage you to take an abstract algebra course. There is an extremely rich and well-developed theory of binary operations with various properties on sets, both finite and infinite. And it is actually a much deeper rabbit hole than you might first expect, right? It doesn't seem like a binary operation on a set is all that complicated of a thing. It seems like it's very general, right? These properties don't seem particularly crazy. They seem kind of nice to deal with. But remarkably, having something as simple as a binary operation and some of these very simple properties lets you say a ton of stuff, like more than we could cover in several semesters of nonstop hardcore lectures, right? People have spent their lives studying this for centuries and have come up with a lot to say about binary operations. So that's my plug for abstract algebra. There's a lot of cool stuff you can do. Next time, we'll go back to our initial motivation from all of these arrow diagrams we drew, where we said, hey, when can you flip the direction of the arrows? And we got some kinds of conditions that would say, here's when I can, here's when I can't, here's when I could on one side but not the other, following paths to get back to where you started. We'll talk about injective, surjective, and bijective functions, the bread and butter of functions. It'll be great. I'll see you around. Have a wonderful day.